Hi everybody, I'm going to talk about how to favor E2 products in this video. So this is kind of the corollary to how to favor SN2 products, where if you want to eliminate SN2 reactions from occurring, this is how you're going to want to get that E2 product as your major. So there's a couple ways you can go about it. The first of which is kind of the opposite of how you do it for SN2. So in this case, we're going to be using a strong base that's a bad nucleophile. Okay, oftentimes that means that we're going to be using hindered or bulky bases. Those bases, because they're so bulky, it makes it much harder to enter close in the molecule to actually access that delta plus carbon and act as a nucleophile. It's much easier and faster to just grab a proton that's just kind of on the outskirts, and then it can resolve its negative charge or its issue, and we end up doing an elimination instead of the substitution. So we'll be talking about some bulky bases today. The other way, which we've kind of already seen, is just to use a tertiary alkyl halide to eliminate SN2 reactions from occurring. So no SN2 is going to be able to happen on a really sterically hindered site. It's just going to be too hard to get into that carbon and do the reaction. The E2 reaction is just going to happen instead. So if you're using something like a sodium hydroxide, sodium methoxide, ethoxide, any of those, you will just get E2 reaction if you're using a tertiary alkyl halide. You will still get E2 as the major product if you're using a secondary alkyl halide in one of those bases, so sodium hydroxide, methoxide, ethoxide. Okay, those are all going to be good options for secondary or tertiary to get yourself to the alkene as your major product. Okay, so let's talk about some hindered bases here. So the first two that I have are very similar here. One is DBU, one is DBN. I'm not really interested in you learning the names, but they do have them in the book if you want to. They're very long names, which is why I tend to just stick with the abbreviation, because without the numbers, this one is diazobicycloindecine, and then this one is diazobicyclononine. So there's a whole bunch going on, and then there's numbers on top of that name. Okay, so we'll just stick with DBU and DBN. They both have a conjugate acid pKa of about 14. Okay, so if we think back to the SN2 nucleophiles in the last video, those were pretty much 10 or below for pKa. So they were not very good bases, but now we're starting to get into better bases here. If we go to potassium tert butoxide, again, we got a nice little bulky bit right there. Then we're getting to a pK of about 17. And if you really want to throw a stick of dynamite in it, you can go with LDA, which is lithium diisopropyl amide. Okay. Amide, that word is used for negatively charged nitrogens as well as the carbonyl functional group. So that gives you a pK of 36. Okay, so these are really serious bases when we're getting down to this type of level. But all of them, they all have in common the fact that they're quite large. They've got steric bulk kind of around the main basic atom that we're using here. And that's going to make it so that it's much harder for it to act as a nucleophile, and it's going to be faster, easier to just get the proton. Okay, so these are not good nucleophiles. Because they are just too bulky. Okay, they won't be able to access the electrophilic carbon. They're just going to grab a proton instead. Okay, and along those lines, this is actually going to be a little bit contrary to what we usually think of as the major product. So if we look at the same example that we used in the SN2 video, or yeah, the SN2E2 video, I believe it was. and I use something like potassium terbutoxide, okay, that if I go through and I label out my alpha, my beta, draw in my H's, okay, so I have my proton positions. These protons, because I've got a methyl group over here, they're just going to be slightly harder to access, okay? Not by a lot, but by enough. So when we have a situation like this, we're actually, and we've got a really bulky base, we're actually going to go for the least hindered side, and that's going to be our major product. So we're going to go for that H, kick off the chlorine, and we're going to end up with that. So the least substituted alkene is our major product. Okay, because bulky bases are going to favor the least hindered side, just because it's faster to make. Okay, so this is definitely a choice between a kinetic product where we're looking at the product that forms the fastest, not necessarily the most stable product, okay? Because this would be the most stable product. And we saw that was the major product when we used something like a methoxy, like a methoxide. But this is going to be a minor product now, as well as this one. Okay, so even though this is the thermodynamic product, okay, that's the most stable. This is the kinetic product formed the fastest. Okay, so if we looked at a reaction coordinate diagram of this, okay, we're all starting from the same starting material. Okay, but we're ending up with different energy levels of products. So we're going to have, this one is A, B, C. So basically what we're going to do here is we're going to have A, C, okay, so that's going to be how I would rank these in terms of stability or thermodynamic energy, if you want to think about it that way. So A, because it's the least substituted, we only have one substituent on here, is going to be the least stable. B is going to be the most stable because it's trans and disubstituted, so it's down here. And then C is disubstituted, but it's cis, so it's right in the middle. So if we think about the energy of activation to get over here, so A is going to have the shortest little hill to go over. That's what makes it the kinetic product. And then the hill for B and C is going to be fairly similar, but we're just going to have, actually I should do different colors here. Oh, why am I still doing the same color? Okay, but we're going to have something more like that. So A is the fastest formed. B would be the most stable, but not formed fastest. Okay, and that's all to do with the fact that your base is going to be clunking into stuff in this molecule when you're trying to access even a slightly more hindered proton environment. Okay, so minor products, major product for at least substituted for the bulky bases. Okay, so also just one final example of just using a tertiary Okay, so if I use this compound and I just go with something small like sodium hydroxide. Okay, I've got few beta positions here. So alpha, beta, beta, beta. So I've got 3 beta positions, a total of 8 protons. So in this case, though, keep in mind this methyl and that methyl, they are basically the same. I do have a plane of symmetry in this. It's not a chiral molecule. So those 2 methyls, whether I grab one H from one, it's going to give me the same product. So I'm just going to have a couple products drawn out here. So I can either have that product or this product. Okay, those are my options. And again, I can rotate this around, but it's going to be the exact same if I have it down because I've got the 2 methyls on the side. Okay, so I've got 2 products possible here. This is disubstituted. This is tri-substituted. So that means that this is going to be my major product. The disubstituted alkene is going to be my minor product, because now that I'm using a small base, right, I'm going to form the more stable alkene. With my small base. And that's going to be my major product. Okay, so I'm going to form the more substituted alkene. Okay, so that's a couple of ways that you can think about isolating for E2 reactions. We're going to keep talking about this for a while longer, so please let me know if you've got any questions, and I'll see y'all later.